Okay, you have seen the interface-based example already. So let's change to the functionality-based characteristic one by using the same example that we have. So we still rely on the same specification and the same program that we have, the getIndexOf method that accepts string and letter as parameters. So if we follow the step in task one, we would do pretty much the same. We identify the testable function of getIndexOf. We identify the parameters of string and letter. With return type is int. The return value is the index of the first occurrence and -1 if no occurrence. And there is no exceptional behavior. So the difference mainly lies in the modeling of the input domain. So in the functionality-based characteristic, we think about the characteristics based on the semantic of the program that we are testing, and we can use the relationship between the parameters of that program. So for example, we have C1, which is the number of occurrence of letter in the string. Okay, you will see that this characteristic combines both letter and string parameters together, and it understands that this function is performing the search of the letter in a string. So we define the characteristic as the number of occurrences of the letter in a string. The second characteristic, C2, is whether the letter occurs first in the string or not. Again, we use the two parameters together. We check whether this letter is appearing at the very first location in the string. So by having these two characteristics, you will see that it is so much different from the interface-based characteristic that you only care about the parameter independently, each one of them, and you only care about the possible value that the parameters can be. With this kind of functionality-based characteristic, we can generate the test cases that are better matched with the specification, and we get more effective test cases. We're gonna see later why is that the case. So if we try to partition the characteristic, we would get as follows. Characteristic C1, the number of occurrence of letter in a string. We can choose several types of partition, but in this case, I choose B1, the occurrence is 0, B2, the occurrence is 1, and B3, the occurrence is more than 1. For characteristic C2, the letter occurs first in a string. I have only two blocks because this is the characteristic that are having only true or false, right? So the first block is the letter occur first in a string, and the second block is the letter doesn't occur first in the string. By having these two characteristics and these following blocks, please pause the video for 1 minute and think about the completeness and the disjointness property. Resume the video when you are ready. Okay, we have seen that by having the first characteristic C1, we have three blocks, 0, 1, and more than 1. For completeness, we check whether if we combine them together, will we get the whole value of the number of occurrence of letter in string back. If we combine them, we would get the number of occurrence starting from 0, 1, and more than 1. And that are all possible value of occurrences of a letter in a string. So the completeness of C1 is satisfied. The second one is we check the completeness of C2. The letter occurs first in the string. So we have two blocks, true and false. So if the letter occurs first, it cannot occur anywhere else. If we combine with the second block, then we get all the potential possible occurrence. So the letter occurs first and it doesn't occur first. So for C2, we also satisfy the completeness. Next, about disjointness, we check whether there are any overlaps between the blocks. For C1, the number of occurrence of letter in a string. So let's say if I draw a number line here, you have 0, you have 1, and you have more than 1. So you have something like this. Okay, this is C1B1, this is C1B2, and this is C1B3. We will see that by seeing this, there is no overlap between the three blocks. So the disjointness of C1 is also satisfied. And the last one, the disjointness of C2. If the letter occurs first, it cannot occur anywhere else, right? And the other way around. So the disjointness of C2 is also satisfying. So next step, we want to identify the all possible values, the possible value as a representative. So for C1B1, the number of occurrence of letter in a string is 0. I picked software engineering and an empty letter, which doesn't occur in software engineering. The second one is the number of occurrences of the letter in a string equals 1. So I pick software engineering again, and now I pick the letter S, which occur only once here. The last block, the number of occurrence of letter in a string more than 1. I pick the same string software engineering, but I pick the letter N, which occur 1 time, 2 times, 3 times. Okay. For this case, you can also select other letter that doesn't occur, like X, Y, C. You would also get the same. You would also still get the same, the representative of the block anyway. So it doesn't need to be only this kind of value that are shown in the slide. For C2, I'm trying to find the representative for C1B1, which is here. So I pick the value of software engineering for the string, and I pick S because S occur at the first in the string. I have only one option here. And you can see that we can also share the test case with the B2 block of C1 as well. For the second block of C2, the letter doesn't occur first in the string. So I pick software engineering again, and I pick T. So for T, it occurs here. So it doesn't occur at the first location in the string, but it still exists in the string. All right. So after this, we continue in task number 2. We want to choose the combinations of the value. We follow the same technique again. We have the number of blocks in C1 and C2. We multiply them, and then we get the total possible test cases of 6. Next, we check for any redundant test or infeasible test. In this case, we would see that this one is infeasible, which means it cannot occur. So if we look into it, we will see that this is a case where the occurrence of the letter in a string is 0. So it doesn't have any occurrences of the letter in the string. But we want it to appear at the first location in the string. So it's conflicting in itself. So you have this kind of infeasible test case. So we just ignore them. The rest are good, so we keep them. So finally, we should have 5 test cases. So based on these test cases, we pick the expected output. So the first case, the occurrence of the letter in a string is 0 times. We return -1. The second case, the letter occur first and also occur once in the string here. So we expect the result of 0. The third case, the letter occurs once, but it doesn't occur at the first location. So in this case, we expect 0, 0, 1, 2, 3. So we expect 3. The fourth case, the string occur more than 1, but it also occur first in the string. So we have S appears in software testing. So it occurred twice, and it also occurred at the first one. And in this case, we return 0. And the last one, we have the letter occurs more than once and not occur at the first. So we have N and software engineering, which occurs 3 times. And the first occurrence is at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the expected output is 10. Okay. Okay. So I think you have seen both the interface-based characteristic and also functionality-based characteristic. I think you can see that the interface-based is simpler and it's very straightforward to derive the test cases. The functionality-based characteristic is a bit more difficult, and you can take into account the semantic of the function or program that you are testing. So let's do another example using both characteristics, and then we will wrap up this module. So in the interface-based characteristic, if we have this new example of another function called triang, okay? The triang function performs the classification of the triangle by receiving 3 integer value of side 1, side 2, and side 3. And it returns the enum of triangle here, which contains scalene, okay, the unequal triangle. Isosceles, the triangle which contains 2 sides that are equal. Equilateral, the triangle that are equal on both sides or 3 sides. And invalid, which is not the triangle, okay? Scalene would look something like this. So the spec says that side 1, side 2, and side 3 represents the length of the side of a triangle. So the return value is the appropriate enum value. So let's start by following the 2 tasks. For task 1, we do modeling the input domain. So the testable function is triang. If we look at the parameters, we have 3 parameters: side 1, side 2, and side 3. The return value is enum of triangle. And the return type. And the return value is that particular enum. Either it's going to be scalene, it's going to be isosceles, it's going to be equilateral, or it's going to be invalid. Okay. And again, there is no exceptional behavior here. If we use the interface-based characteristic, we model the input domain directly based on the parameters. So we have 3 parameters here: side 1, side 2, and side 3. So I create 3 characteristics as well. The first one, characteristic C1, the relation of side 1 to 0. Characteristic C2, the relation of side 2 to 0. And C3, the relation of side 3 to 0. I care about 0 because the triangle cannot have the sides of negative value or 0 value. Okay, so I put some intuition and understanding of the triangle here. Let's say we have these 3 characteristics. So next, I'm going to create the partition. For each one of them, I create 3 partitions. So for C1, I have block B1, which is side 1 is greater than 0, block B2, side 1 equal to 0, and block B3, side 1 is less than 0. And I apply that to all the other characteristics, okay? So if we look at the number line, we would get something like this. We have 0, we have 1, so B1 is greater than 0, B2, or C1, B1. This is C1, B2, and this is C1, B3, okay, less than 0. So by having these 3 characteristics, the next step is to check for completeness and disjointness property again. So let's pause the video for 1 minute and think about this, and then resume when you are ready. Okay, I hope that you would see that the 3 characteristics are actually complete and also disjoint because there is no overlap between the blocks. And when you sum them up, you get the whole input domain of each characteristic back, right? So next, we are trying to identify the potential possible value for each of the block. So for block 1, the value that are greater than 0, I select 7, 3, and 2 here. For block 2 of the 3 characteristics, I can select only 0 here. And for block 3, the value that are less than 0, I can pick -3, -1, and -2. But if we look at this value, actually the one that are valid triangle is only one combination here. Because these are not valid triangle, and these also cannot generate valid triangles. So this is one of the potential problem with interface-based example. It doesn't take into account much semantic about the function that we are testing. So let's try to refine the characteristic a bit. We want to get better test cases which cover more valid triangle. So I changed the block as follows. So for characteristic C1, I have the block B1 of greater than 1. I have the block B2 of greater equal to 1. And block B3 of equal to 0. And block B4 of less than 0. For C2, I have the block B1 of greater than 0. I have the block B2 of equal to 1. And I have the block B3 and B4 similar to the previous characteristic. And for C3, I also have B1 of greater than 0, B2 of equal to 1, and then B3 and B4 are all the same. So let's pause the video again for 1 minute and think about the completeness or disjointness problem here. I give you a hint that there is a problem with disjointness here. So what is the problem? All right, if we look at the characteristics C2 and C3 and look closely at B1 and B2, we would see that there is a disjointness issue here because the value, one value is greater than 0. Okay, so this is C2B1, and one value is equal to 1. So you got some overlap here, right? So this overlapping of block B1 and B2 of characteristics C2 and C3, it violates the disjointness property, okay? The completeness is okay. When you sum everything, you got the whole input domain back. But for disjointness, the first one is okay, but the second one and the third one is not okay. So how should we fix it? We fix it by changing this to be similar to characteristic C1, and then the disjointness is gone, because now you pick the value that are greater than 1, the value that equals to 1, value that equal to 0, and the value that less than 0. So everything is good now. So by fixing this, next we proceed with finding the possible value. So for B1, we want the value greater than 1. So you get, let's say I get 2, because I pick the value that are closest to the boundary. It is greater than 1, so I pick the integer 2. Okay, I want to test more at the boundary value. Similarly, for B4, I want the value that are less than 0, so I pick the value that close to the boundary as well, which is -1 in this case. And for B2 and for B3, I can only pick 1 and 0 because it is exactly specified by the block B2 and B3. Okay. By having these 3 characteristics and 4 block each, if we compute the amount of total test cases, we would get 4 multiplied by 4 multiplied by 4, and then we would get 64 test cases, which is a lot. Like here, 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 so on and so on. Okay. So there are many test cases which we don't actually need these many test cases. And we can see that most of them, these are invalid triangle. These are also invalid one. Okay. And we get some valid triangle, but there might be too many to test, and you are testing pretty similar test cases over and over again. So let's see how can we make this better by using the functionality-based example. So by applying the functionality-based characteristic to the same function here, the triangle function, we would follow similar task 1 of modeling the input domain. We have the triangle method to be tested. We have 3 parameters of site 1, site 2, and site 3. The return type is enum, and the value are the enum value of each triangle type. There is no exceptional behavior. So the key difference is how we define the characteristic. So in this example, I define just one characteristic, C1. C1 of my characteristic is the geometric classification of the triangle, okay? And first, I partition it by having 4 blocks, B1, B2, B3, and B4. I put the first block of scalene. I have the second block of isosceles. I have the third block of equilateral, and I have the fourth block of invalid triangle. However, if we look into the block B2 and B3, when we do the disjointness property check, we will see that they are not totally disjoint. Because if we just say isosceles and equilateral, we can also say that some of the equilateral and all of the equilaterals are also isosceles because there are at least 2 sides that are the same. So we refine the characteristic a bit, and then we get these final blocks. B1, scalene triangle. B2, isosceles, but not equilateral. So we get rid of the overlap. B3, equilateral triangle. And B4, invalid triangle. So next, I would identify the possible value. For scalene, I pick 4, 5, 6. For isosceles, not equilateral, I pick 3, 3, 4. For equilateral, I pick 3, 3, 3. And for not for an invalid triangle, I pick 3, 4, 8. Do you know why it's 3, 4, 8? It is 3, 4, 8 because one of the property of the triangle is saying that the 2 sides sum together must be more than the other side. So if we pick 3, 4, and 8, we would violate this property of the triangle. 3 plus 4 is not more than 8, right? Can we have other possible characteristics? Yes, you can use your own creativity to find out other characteristics as well. This is just one of the possible potential characteristics that you can have. So by having this, we have much simpler test cases with just only 4 combinations. Okay, C1B1, C1B2, C1B3, and C1B4. And we get the test value and we put the expected result here. And we can see that by having just 4 test cases, we cover all the types of the triangle, much better than when we do these 64 test cases of interface-based characteristics that we might not even cover all the types of the triangle, right? So this shows that by using functionality-based characteristic, we take into account the understanding of the function that we are going to test, and we can get better test cases. Okay, so to summarize, there are 2 types of input space partitioning technique, which is a technique that we use to partition the input domain into smaller chunks and to create test cases for each one of them. The 2 approaches include first the interface-based characteristic, where we define the characteristics based on the parameters independently. It is straightforward, easy to do, but the weakness is that you might get some unusable test cases or the test cases that are quite redundant. The second one is functionality-based characteristic. It incorporates the semantic of the function to be tested into the design, and you get better test cases. The weaknesses is that it might be more difficult to design, and it might be more difficult to generate the test cases as well. And that is pretty much it for this module. I hope you understand the ISP technique, and then we'll try to do some exercise in class.